I would like to switch to our last speaker today before the session, who is John Pritchard. First of all, John, thank you a lot for setting up the whole meeting. And so please go ahead with your analysis and presentation of the UVES operational history and statistics.
Good afternoon, good morning, and good evening, wherever you are in the world. It's kind of bizarre to say thank you, since as Luca points out, I sort of set it all up. But anyway, I'm here, and I'd like to talk to you about the perspective of UVES from the operational side. This first slide I'll gloss over rather quickly because Sandro already covered most of it earlier. The project began in the 80s, and then in the 90s officially the kickoff meeting. PDR sometime, well, in October 1993. 1994, they changed the decision to make only one UVES. When I actually discovered this only in researching this presentation, that the original plan was to have two UVESs, and I was intrigued by that idea that we could have had one UVES. And then I realized, of course, that they would have not been the same UVES as we have. So I'm happy that we have the one UVES with the improved capabilities that it has today. The FDR, I guess, was sometime in 1990 something. Didn't quite find that, and maybe the procedure wasn't so well defined back then. It was interesting to note, I think, that so the system test was performed in 1999 in May, and the instrument was flown to Paranal, or at least to Chile, and then assembled, integrated, and verified in what probably seemed at the time like 4 very short months. So, as I say, a assembly, integration, and verification was completed late 1999. First light was taken on September the 27th. This wasn't, I don't believe, the very first spectrum taken with UVES, but it was one of those taken in that first light campaign. It is supernova 1987, and a kind of iconic image, and it's been used for the logo for this workshop. So already from the very first, it was clear what the potential of UVES was, and that it was performing exactly as it was expected. Commissioning was then carried out in October and December of 1999 and January of 2000. Science verification was carried out and completed successfully also in February of 2000. And oops, wrong way. And then science operations were due to start in 2000, April the 1st of 2000. But in fact, that's not what happened. Science operations started half a month earlier, back in March the 13th. If you go to the Science Archive facility today, you can find the very first publicly available science image from UVES is indeed from that day. And since that day, we've now been operating almost continuously with hardly any interruption. And that's the main topic of my talk today. So 2000 officially, April the 1st, we started operations. And UVES really has been, if anything, the one word one could say is stable. And that's been part of a major part of its success. And the timeline that I'm about to show you with not very many points will illustrate why. So from day one at the telescope, everything was in place. We had P2PP, which I'm sure many of you at least are very familiar with, from period 60, the very first images of what that looked like. UVES had a pipeline, a functional working pipeline at the telescope that provided real-time reductions that could be used to check the quality of the observations online. And it had quality control right from the beginning, which meant that the high standard of data could be assured right from the beginning. In 2002, Flames UVES was added to the suite, or Flames was added to the suite of instruments at Paranal, including the fiber link, giving Flames UVES adaptation. In 2004, we added rapid response mode. And we also changed the blue CCD, to improve the performance of that CCD. In 2005, the cross dispersers, not the cross dispersers were replaced, excuse me, the worm drives of the cross dispersers were replaced. So not the actual optical elements themselves. In 2006, we added long slit mode, which allows you to have a much longer slit than is dictated by the separation of the orders for specialized purposes when you need the high resolution in a very specific wavelength range, but you want some much more spatial information than is normally available from UVES. In 2007, we also added the ultra-fast readout mode. In 2007, from a processing side, we released the first version of the CPL pipeline, so not the Midas pipeline. This was fairly seamless thanks to extremely hard work from our software developers who implemented and mostly, well, so I shouldn't say mostly, improved many of the functionalities of the pipeline. In 2009, we took 2 months to upgrade the red CCD mosaic. This was one of the chips in the red CCD mosaic. So it was a major upgrade, which at least at the longer wavelengths improved the quantum efficiency by a factor of 2 and even more, and made a major improvement in terms of the fringing effect that was seen in the chips before. The red line was the new chip that is still in place. The black line was the original chip used in UVES. So the fringing was much improved by the upgrade. 2010, the ESO Reflex was released, and it was released with one workflow, if I remember correctly, and that was the workflow for the UVES Blue, for UVES Blue reductions. UVES Red was added, I think, 1 or 2 years later, and since then, most of the other ESO instruments have been added, have had support for ESO Reflex added to them. But UVES has had that support even now since almost 10 years. There's the original workflow for ESO Reflex for UVES. In 2011, we also replaced, again, not the dispersers, the cross dispersers themselves, this time the blue arm, but the worm drives for the cross dispersers. So again, no change in the optical elements, of course. And in 2015, a particularly interesting milestone was reached. We had an extraordinary maintenance after almost 10 years of uninterrupted operations, which is, I think, an outstanding achievement for any instrument. In 2017, after a particularly nasty earthquake did move things around quite a bit, and we were having a lot of trouble with the resolving power in the blue, we had another intervention which managed to restore the resolving power of UVES in the blue arm all the way back up to 90,000, its original resolving power, and perhaps even arguably never before achieved resolving power right from the beginning of operations. But this full length of time plot of QC data, the control data from UVES, shows the lifetime of the resolving power. And you can see it has a gradual trend down, which I guess is due to a gradual degradation of resolving power through dust accumulating and such things. But it is clear that we are able to restore that from time to time with major interventions. So that's good news. In terms of the red and the red arm on the 2 chips, we have 2 chips. Sorry, they probably can't see it. I'm changing it too quickly. The situation is a little bit different. Go this. I'm going the wrong way here. No, back this way. There we go. So blue, red, and the other red chip. The situation here is a little bit different. It's always been a compromise between the 2 chips because the 2 chips are mounted independently. It's always been a compromise to maintain the resolution between the 2. But you can see at the moment we're in a very healthy situation with both chips having very good resolving power, and almost at their expected 110,000 maximum. So that's basically the operational history in terms of interventions and things that we've added and maintenance that's been carried out on the instrument. And as you can see, it's a very short list, and that I think is a very great contribution to the success it's had. And as has been mentioned a number of times this morning, UVES's stability is a major factor in enabling the science that it can do. And my last point is a question mark for what will happen in another 20 years, what the equivalent presentation will look like in another 20 years, because I think UVES certainly can go that far. I'll move on now to statistics. Here, I've compiled statistics essentially from considering all of the science files that are in the Science Archive facility. So these are all publicly available, except for those that have been obtained in the last year. Although these statistics include those, because I can get at those, of course. There's some caveats that need to be considered, which is that these will invariably include some tests that were done during the daytime. So science files that managed to get in during the daytime probably won't include a lot of 2-hour exposures that were done during the daytime, but there will be, it's not 100% accurate. It also, in terms of the exposure time that you'll see in a minute, you have to keep in mind that we count I have counted for these statistics, every single file. And since we have the dichroic modes where most often both the red and the blue arm are acquired at the same time and therefore produce 2 independent files, the exposure time of those two files get counted together. So they add. So although we're exposing, the shutter effectively is only open once, but we've counted the time twice. So there's caveats to be made. On the other hand, that comes later, sorry. That's in terms of the OBs. So let's get on with the statistics. The first one is that over the lifetime of UVES, we have supported and executed some 2,000, at least one OB, and acquired at least one science exposure for 2,787 programs. You can see the breakdown there in terms of service mode and visitor mode. It's about a quarter of the runs are in visitor mode. Looking at this graphically over the period from 2000 to 2020, you can see that clear trend. If we compare it, the different modes, the different observing modes used for UVES. So here I'm comparing Echelle versus Flames UVES MOS mode, multi-object spectroscopy, and any of the exotic Echelle modes, such as using the slices or using the iodine lamp or the long slit spectroscopy modes. You can see that Echelle in the blue is evidently quite a lot more used than MOS mode, and finally all the other modes. So the clear dominance of the normal Echelle, the main mode. After that, after visitor mode runs, we have the number of OBs, some 41,290 OBs in total. Here, this will be an underestimate because in visitor mode, individual OBs can be repeated over and over again. You may want to follow one object throughout the night. You design one OB and you just keep re-executing the same OB over and over. Although that will produce distinct files, it's counted as one OB. So 41,000 is a lower limit to the total number of OBs. Again, we see service mode versus visitor mode, similar trend. And again, the number of OBs for the 3 different observing modes, Echelle versus MOS versus the, as I call them, exotic modes. After that, so those 2,700 runs with 42,000 OBs have resulted in some 204,488 science FITS files in the SAF, in the Science Archive facility. And that is, as Javier said, being added to even now with our minimal science operations mode already making progress with UVES. All of this comes to a grand total of 4 years of open shutter. So as I said, caveat here, we're counting each. So the fact that we're observing in both red and blue at the same time means we're counting double. But we have 4 years of open shutter out of 20 years. So we're talking 20% of the time. This service mode versus visitor mode, only in the first year of operation in 2000 did visitor mode, was visitor mode used more than service mode. Since then, it's been the usual trend, at least in terms of hours observed. And again, the same trend that we've seen in all the previous plots for Shell versus Moss versus the exotic modes. If I can just elaborate slightly on the 4 hours, so 4 years. So if you consider and roughly estimate that approximately half the time is dark, then that in fact means that not 20% of the time has been used, not 20% of the available time has been the shutter been open, but in fact more like 40% of the available time has been open. And then if you consider that UVES has since day one shared UT2 with at least one other instrument, it was brought into operations at the same time as Force 2, and so it's had about roughly half of the time allocated, or half of the time available has actually been available to UVES. That's another factor of 2. So the actual fraction of the shutter time open compared to the amount of time available to UVES is something like 80%, which I think is absolutely phenomenal. After all of that, so that's all the time that we've spent collecting photons, we get, of course, to the bottom line, which by most people's reckoning will be, of course, the publications. Sandro touched on this already a little bit earlier. So here we are basing the statistics that I'm about to present on the ESO telescope bibliography. And according to the ESO telescope bibliography, UVES has published some 2,243, sorry, not UVES has published, but there are some 2,243 publications featuring UVES observations. Graphically, it looks like this. But of course, what is a plot like this if you can't see that in comparison to other instruments? If we compare, first of all, the 2 instruments that arrived before UVES in 1999 on UT1, Force 1 and Isaac, and we see that they both had similarly steep initial climbs, rises in publications, but have not managed to maintain that. And of course, being removed from the telescope certainly hasn't helped for those instruments. Arriving at the same time as UVES, of course, was Force 2. And we can see that it's done fairly well, almost as well as UVES. Since then, we've had a couple of other instruments that have come close to, but do not yet rival UVES, but may do with time. We have X-Shooter, which is certainly a strong contender, a strong publication record. And we have Muse, which is a very strong contender. And in fact, I just noticed now, looking at my graph closely, that in 2020, Muse has beaten UVES. So for the first time, apart from in those first years when Force 1 was ahead of UVES, an instrument has actually beaten UVES. The rest of the instruments for the VLT sort of fill in all the rest of the space with varying degrees of success. If we look at this from another direction, in terms of number of publications, number of publications from the year of starting observations, then we can see that indeed Muse is a strong contender and is indeed ahead of UVES at the same time. So you all need to get out there and publish lots more papers using UVES data and not using Muse. Thank you for that. Yeah, so that's for publications. To make a summary, and this was supposed to appear one thing at a time, but never mind. Okay, so what do I think UVES is? It's a stable instrument. It's had very few interventions. It has maintained one of its primary characteristics, its resolving power, relatively stably over the years. And we've shown that we're able to intervene and restore that as it does drift with time. We have a stable yet adaptive operating model in the sense that UVES operations at the telescope have hardly changed over the years, and yet at the same time we've been able to add in rapid response mode, flames UVES, different observing modes, add in the long slit spectroscopy, etc., and absorb that within the existing operating model and continue operating UVES in as stable a mode as it is. It's an extremely productive instrument. As I said, you can estimate that it has an approximately 80% open shutter time fraction, and it is one of the most, if not the most, productive instruments, at least on the VLT, in terms of its publication record. So what has UVES done? I believe it has more than completely and more than fulfilled its mission to date, and I believe it has a very bright future ahead of it. And if we can make some upgrades, then maybe that will become even stronger. That's the end of my presentation.
Thank you a lot, John, and actually thank you for the talk and thank you for setting up also this workshop, and really thank you.
Welcome.
One question I have, I'm sorry if I miss it. Do you know anything about downtime? I mean, does it result kind of problematic from the downtime point of view, technical downtime of the instrument I'm talking, or because I think it's pretty okay, right?
Yeah, the amount of downtime is very limited. It's very difficult for us to. This was one of the things that I asked that amongst the three of us that prepared this, that I asked that we try and investigate, and it's really hard to find it. We as an observatory, we haven't kept track of that very accurately. It's in tickets and so on, but it's really hard to find. We don't have an easy way to get statistics on it in a reliable way, like we can for the shutter time and so on. But anecdotally, I've been involved with starting as the QC scientist and then in USD since 2006, and the amount of time that it's offline for any real problems is extremely small and limited as compared to other instruments, not mentioning any names, of course. We had, as I said, there was the 2017 intervention when we restored the efficiency, not the efficiency, I beg your pardon, the resolving power back up to 90. This was largely motivated by the earthquake, which caused some severe problems. These were especially prevalent in the blue, which affected things strongly in the blue. So a number of our programs were no longer possible, but we could still do some things. And we privileged doing things in the red. So the versatility allowed us to keep going. So despite the fact that the resolving power was in some ways and for some slit sizes and so on, down by a factor, a significant factor, because of UVES's versatility, that hardly shows up at all as any technical loss.
Yep. Thank you. Annalisa, yeah. I see that has a question.
Yes. Yeah, thanks, John, for the very nice talk and report. Very impressive, this statistics on the open shutter time. I was wondering if you can comment on the time when UVES is on focus, and specifically after X-Shooter came online and in the same unit. Did that change?
Certainly, the pressure on X-Shooter is huge, and it has. I mean, UVES and X-Shooter have been on the same telescope for a number of years. Not always. There was a time when X-Shooter, I think, if I remember correctly, X-Shooter came first to UT2, then it was moved to UT3, or perhaps it went directly to UT3. Maybe Luca can answer that. But for the past few years, it has been on UT2. Just before coronavirus struck, we started moving it back to UT3. But certainly during that time, UVES has, to an extent, suffered because of the popularity of X-Shooter. X-Shooter is an extremely popular instrument, and it has taken a lot of the time available at UT2. So estimating that UVES has available 50% of the telescope time is overestimating, that's for sure, because if you simply balance the amount of time allocated between the two instruments, requested, allocated, and then observed, it's probably somewhat below 50%. On the other hand, well, I mean, they are quite complementary, as we've seen from at least one presentation mentioning that UVES and X-Shooter can be used together, one taking the fainter targets, X-Shooter taking the fainter targets, and UVES being used on the brighter targets. So there's, I think, healthy competition, as well as at the same time complementarity. So it's certainly
John?
it has taken a hit. Yep.
Sorry, I would like to proceed. There is a last question because I don't want to go, much over time, particularly for our Australian friends. And Annalisa, thank you. I hope it was okay, the answer.
Thank you. Thanks.
Stefano?
Yeah, I had a question about how much is the ultra-fast readout mode used?
Not much. Not much. Part of that is because for the first, I can't remember how many years, it was only available in visitor mode. We have, and I think it is available now. It can, I think we discourage it still. It's still in service mode, but it is generally accepted if somebody can justify it with a waiver, basically. So that has limited its.
And what are the typical programs there it is used for?
Off the top of my head, I cannot remember because there have been so few programs.
The only thing that comes to my mind.
What I missed your. What did you say, Luca?
Stellar oscillation, pulsation. I mean, when
stellar
you
oscillation. Okay.
Yeah, I guess so.
Yes, this is exactly the case. We had a few programs for doing very fast, very short spectra of very bright targets.
Yeah.
But it's not very common.
No.
Okay.